A very good evening to Dr. Ng. So today I will be presenting about ordinary differential equation. So an ODE is basically a equation that contains only one independent variable and one or more of its derivatives with respect to the variable. It is used in many different industries in our daily life and has many physical laws and relations appear mathematically in the form of differential equation. Below are a few examples of daily applications. These are the two types of order of ODE, which are the first order and second order. These are the few types of ODE, and these are the few methods to solve ODEs that I will be explaining further at the back. The first method is separable ODE. A separable ODE should be written in the form of fy dy equals to fx dx, where dy is a function that depends solely on the independent variable y, while dx is a function that depends solely on the independent variable x. Below is an example of a separable ODE. Next is a homogeneous method, which is a method to solve ODE that are not separable. It can be written in the form as shown in the slide, and m and n must be a homogeneous function with the same degree. Once they are homogeneous, you can sub in y equals to vx and solve the equation to make it separable. The third one is an exact ODE. It can be written in the form shown in the slide, and to satisfy its condition, the derivative of m in terms of y, it should be the same as derivative of n in terms of x, while the opposite of exact is non-exact. The derivative of m in terms of y shouldn't be equal to the derivative of n in terms of x. So by doing so, we have to multiply it with an integrating factor of fx or fy so that we can convert it into an exact ODE. Once we get an exact ODE, we can just solve it using the same method as an exact ODE. Next is a homogeneous linear ODE. It should be written in the form as shown in the slide, y prime plus px y equals to 0, where non-homogeneous linear ODE is the opposite, which Rx doesn't equals to 0, so we have to solve it by using the integrating factor method. Lastly is the Bernoulli's equation. We have to sub in the formula to find u prime and to find the value in the small box shown in the slide. Once we get the small box value, we can just proceed with the integrating factor method. Lastly, the real-life modeling question. Given a population of a town grows proportion to its current population, the initial population is 7,000 and grows 7% a year. The goal of this question is to find out the model of the question and the population after a certain period. So first we have to come up with a modern question to solve, which is shown in the slide, dp over dt equals to 0.07p. Once we get the modeling equation, we have to solve it by integrating it. The steps of integration is shown in the slides, and lastly we can get the final modeling equation, which is pt equals to 7,000 e power of 0.07t. In order to find the population after a certain period, we can just sub in the t into the final modeling question to find the final answer. So that's it from me. Thank you.